much for a very kind invitation. This is this has been such a pleasure to watch the video of other speakers. This is really an incredible workshop, and I'm very honored to be among the speakers. And I'm learning a lot. And I want to start with acknowledging an intellectual debt to Daniel Dennett, who I got to him much later. Being a computer scientist, I discovered him only a few years ago, and I was very much influenced by his thinking and his writing, and in particular the book From Bacteria to Bach and Back has been extremely influential on my thinking, and I think I can use it to as a springboard for my talk, because subtitle is the evolution of minds, and I think the evolution is something that was very dear to Dennett, and I think in my thinking it's been also very important, because if we look at the phylogeny of intelligence, what we realize is that the modern things, the things like language, abstract thinking, symbolic behavior, they're very recent, right? They are basically, the last 5 minutes, evolutionary speaking. The vast majority of the time we spend developing much more simple, much more primitive understanding and model of the world through our physical senses. Okay? And so when we talk about AI, the current dominant paradigm, the one that works so well right now, is the one that starts with language, right? The large language models that you you start top down. You said, okay, we have 2,000 years of human culture. Let's feed it into the computer and figure out what happened. And then the hope is that, starting with that, we can get to the nitty gritty, the pixels, the sounds, the touch, the torques of the robots, etc., etc. And I am not sure this might be the only, or maybe even the right way to proceed, because if we remember Moravec's paradox, for those who don't know, the simplest way to state it is, in AI, the hard things are easy while the easy things are hard. And so the example I put here is a classic example of Garry Kasparov losing to Deep Blue about 25 years ago. And you can see that, right now, computers completely beat humans at chess. But even now, in 2024, we don't have a single robot that could actually move the pieces on the chessboard reliably. Okay, so here you can see a guy moving the pieces, and even now, there is no generalized version of a robot that could do this task. So the hard things turn out to be easy, but the easy things turn out to be hard. And so what I'm attempting to think about, and a bunch of us kind of working on sensory motor AI, are basically trying to look at it from the bottom up. We ignore language and we start with the low the physical sensors, the pixels, the sounds, the touch, the torques, and try to see how far we can get in this kind of bottom-up, emergent kind of a evolutionary way. Okay, and my own personal interest is mainly in computer vision, and so you can ask, why am I even talking at this workshop? Well, I guess I have a little bit of a bona fides in the very distant past. As part of my PhD thesis, I had proposed an autoregressive model on pixels. So before LLMs were cool, what we did here is we said, okay, can we synthesize visual textures one pixel at a time basically, given that we have some sort of context, how do we synthesize pixel P? Well, we can assume that the Markovian property that probability of the pixel P only depends on the neighborhood of P, basically the context in the current LLMs. And the only difference is that, at least back then, it was impossible to kind of compute the probability tables for all the possible contexts. Something like n-gram for pixels would be too big. And so we basically just sampled from the original data directly, and then just like, okay, find the closest neighborhoods and just copy a pixel from one of those closest neighborhoods at random. Okay, so super, super simple, trivial, some would say, non-parametric sampling autoregressive model. And kind of the surprise was that it worked pretty well. So here is an example of what happens when you start with an image on the top, and then you basically have a small context, a little bit bigger context, bigger context, bigger context. You can see kind of similar things happen with the modern LLMs as you vary the context. The smaller the context, the more local interactions, the dumber it is, and then the bigger the context, the more information you get. And then you can do things like in-painting, you can do things like out-painting, okay? And so basically, doing that made me realize that given that the algorithm is so simple and so trivial, really, and the results were, at least at that time, that they were much better than anything else in the community, I started thinking, okay, where are the smarts? And I realized that the smarts are really in the data. And so for the last 25 years, I've been really single-mindedly focused on trying to understand the data. Okay, and this is what I thought I would talk about today, and maybe try to convince you, if you're not yet convinced, about the magic that is in the data. Okay.
Alyosha, can you first define in-painting and out-painting for those who have no idea?
Oh, sorry. In-painting is where you have a hole and you fill in the hole, right? So you have an image like this, and you have the black pixels are not present, and then you basically just use your autoregressive synthesis to fill in those pixels. And out-painting is the same thing, except your hole is on the outside of the image, so you paint things out. Okay, so you can imagine that you can do the same thing. In fact, you can do the same thing with LLMs. Just fill in the blanks basically using an LLM. In fact, people have been doing this quite successfully. Okay.
Thank you.
Yep. Okay. So much of the magic is in the data. So let me set the stage. Let's imagine that we are in Paris, and we went to the Musée d'Orsay, and I just been there a couple of weeks ago, and this wonderful painting, Gare Saint-Lazare, is hanging there, and it's a really wonderful example of impressionism, because you really feel like you're at this turn of the century train station, and you have kind of feel the hustle and the bustle of the trains, and this steam engine is approaching the viewer, kind of coming straight at you. It's very immersive. But if you look at the steam engine, you realize it's just a splotch of paint on a canvas. It looks more like a penguin or a bottle of champagne, right? Where is the steam engine? Well, the point is that the steam engine is not really in the pixels. The steam engine is in all of our experiences and memories, and it's very likely that all of you are seeing a slightly different version of the steam engine, depending on which steam engine museum you went to as a child. Okay, so basically the human brain is really good at hallucinating the stuff that's not quite there. And here is a beautiful video produced by Antonio Torralba, a very good friend from MIT, and here's Rob Fergus working at his MIT office, and it's a very blurry video, but you guys have no problem understanding what's in it, right? In fact, your brain is so good at filling in the holes in the perception that actually you realize that you filled them in not quite right, because Rob is actually talking on his shoe, and now he's listening to his beer cans, working on his trash can with his stapler. Okay, and we didn't see any of that because the brain took over. Okay, so Moshe Bar likes to say, our perception relies on memory as much as it does on incoming information, which blurs the border between perception and cognition. And Lance Williams says, mind is largely an emergent property of data. So I'm not sure I completely agree with him, but I think I see the point. And at least in, I come from kind of computer science, machine learning tradition. In the old days, we as a community did not really appreciate that. For us, the most important thing was the algorithm. That's how you get papers published. That's how you get your tenure. That's how you get people to know you. It's all about the algorithm. You come up with a clever idea, you work on it for a year, then maybe like, a month before the deadline, you need to come up with some features, and then maybe like a couple of days before the paper deadline, you say, oh, I need to run it on some data. Let me find some data. Okay, boom, data. Okay. And this kind of like a Maslow pyramid, in my argument is actually it's inverted. It should be the other way around. And so let me give you a couple of examples from computer vision that kind of illustrate my point. So computer vision did not work at all when I started graduate school. So computer vision was a very sad, lonely endeavor. And then somehow in the late 90s, things started to work. And maybe the first thing that really made things work was face detection. You give a computer an image and boom, it will detect faces. Okay. And if you go to your computer science, computer vision colleagues and you ask them, okay, what is the paper that made this jump, that boom, made things work? And most of the people will tell you, and it's in all the computer vision textbooks, it's the paper called Viola and Jones. That's the famous paper. Maybe you have heard about it. But actually, that's not quite true. In fact, there were 3 papers that all came around the same time. They all produced algorithms that worked very, very well. Raleigh Baluji-Kanadi was the first one. Schneider-Kanadi was doing the best. And Viola Jones was a real time, although by that time, I think Schneider-Kanadi was also real time. All 3 are actually respected in the community. All 3 got the best test of time awards. But the kind of the historically, as a community, we only remember Viola and Jones. And the reason for this, I claim, is because Raleigh Baluji-Kanadi used this very, very old kind of discredited idea of the neural network. In the 90s, nobody wanted to have anything to do with neural network. It was this old thing that didn't work. So it was not sexy. Schneider-Kanadi, naive base. Also not sexy, very naive, right? Viola and Jones, they had this beautiful algorithm called the boosted cascade. I still teach it in my machine learning class. It's a beautiful, gorgeous algorithm, very nice. But was it actually the thing that made it work? No. Here are 3 methods, were completely different approaches, pretty much the same performance. So what made it work? Actually, it was the data. In particular, these were the first 3 papers that realized that if you want to detect faces and images, you want to have data not just of images with faces, but you also want to have negative data, images without the faces. And basically all 3 papers made this leap, and suddenly things started to work. So I call this our scientific narcissism. All things being equal, we prefer to credit the performance to our own cleverness, to our own algorithmic design, because that's a product of human generation. Whereas data, well, it's just there. It's in the physical world. You cannot really take credit for it. And I think this has led us to some scientific hubris that is only now we're trying to unravel. Okay, there is a wonderful paper from about 15 years ago out of Google called "The Unreasonable Effectiveness of Data" that makes the point that while parts of our world can be explained by elegant mathematics, physics, chemistry, astronomy, there is a lot that cannot. Psychology, genetics, economics, and one would argue AI. And the reason is basically that these are things that are somehow connected with evolution, right? They're biological generated fields, which basically the process of evolution injects a lot of entropy. There is just a lot of junk being generated as part of this noisy evolutionary process. And this is exactly the fields where the magic of data seems to work. So kind of to maybe explain this a little bit in a more visual way, imagine that you are in your computer graphics, you're working for some movie studio, and you want to do a computer generated visualization of smoke. Well, smoke as a physical phenomena, it's actually pretty easy to visualize it. Just plug it into the Navier-Stokes equation and simulate it, and you get this beautiful, realistic looking smoke. Okay, but imagine on the other hand that you want to do computer generated version of a bark of an old tree. Okay, this turns out to be very, very, very hard in computer graphics. Why? Because we don't have a closed form solution for what the bark on a tree looks like. Now, there is probably some sort of parametric form, but it will have tons and tons of parameters because it will depend on the genome of the tree, on the weather, on the location, whether you have a squirrel in this tree, etc., etc., etc. It's very, very complex process, right? And fundamentally, it actually goes back to this problem of how do you even define a tree? What is a tree, right? And as Wittgenstein pointed out, this is really, really hard, right? Any kind of definition you can try to come up with, and you give it to the computer to try to recognize trees, it's going to fail because there is a lot of things that fit the definition and are not trees, and vice versa, right? So it's hard to give a good definition of a tree, yet any 3-year-old can tell you a tree from a non-tree, right? So the 3-year-old is not using the definitions. The 3-year-old is learning from the data. And so this is really why I believe we have such an amazing success of these data-driven approaches, because oftentimes this is a much better way to describe kind of evolution-driven processes. Okay, and the good thing is now we actually have a huge amount of data. The data is just raining down on us, and with enough data, what we find is that even really, really brain dead, basically data lookup, already works surprisingly well. Okay, so I'm going to give you a few examples from the visual world. For example, this is probably one of the most influential paper in computer vision. It was rejected from every single conference at the time because it was so revolutionary. And this is where Antonio Torralba and his colleagues asked the question, okay, how many images does a 5-year-old see? Okay, and they basically came up with an idea with a count of roughly 80 million. Okay, and so they said, okay, we'll just collect 80 million images. Okay, and this was before ImageNet. This was very, very early on. And maybe if you have heard of the CFAR 10 or CFAR 100, these are just tiny little snippets of that grandiose 80 million data set that Antonio and colleagues have collected. And what they found is that as you get more and more data, as you increase your data, you find examples that are very, very similar to any given image that you give it. Okay, you start seeing that your nearest neighbors become very, very similar to yourself. And they they show some cool examples. So they basically, also collected it in the word net hierarchy, and then you can actually kind of do recognition by simply just voting, kind of nearest neighbor voting. Given an input image, you basically kind of say, look at its nearest neighbors, and then you can vote on the word net hierarchy and say, okay, entity, object, living, organism, person, scientist, chemist. Well, I'm not sure about chemist or even scientist, but definitely a person. And this was done with just a brain dead lookup. Nothing, no smarts here at all. Just basically finding the closest images. Okay. Around the same time, me and my student James Hayes have been doing something similar on the graphics side. Let's say that you have an image and you want to get rid of this part, and then you want to fill in the hole. And so what we find is, again, we downloaded about 2 million images from the internet, and we tried to find the most similar image and then see if we can basically use that image to fill in the hole. And there's a little bit of computer graphics magic, but there you go. Fill in the hole. You can fill it a different way. Here's another way. And sometimes it doesn't quite work, but you get the point. Okay. And if you don't like the view out of your window, you can replace it, etc., etc., etc. Okay. Here's some more examples. And why does it work? Again, it's not about our algorithm being super clever. It is really about the data. In fact, the story was that we started with what was the largest data set of the time was maybe like 1,000 images. So we downloaded 20,000 images. So by far the largest data set in 2007. And we tried to see if we could look at the nearest neighbors given these data set of 20,000 images, and you can see that the nearest neighbors were really not that near at all. They were pretty far. And this was at the end of December. And so the deadline for the conference was in January. And I told James, I said, you know what? Why don't you just make the computer keep downloading images while we go on the Christmas break and see what happens in January. And in January, we had 2 million images. James ran exactly the same algorithm, no change in the algorithm at all. And boom, the nearest neighbor started to look much, much better. And then the whole thing just worked. Okay. And the following year, we had a kind of the same kind of idea, but for the task of geolocalizing images. So given a photograph, the question is, can I predict the GPS location? Can I predict where this photograph was taken? And again, what we did is we downloaded, in this case, 6 million images. This is like, 6 times more than ImageNet. And start basically have them vote on the whole surface of the Earth. And the idea is that if there is some pattern there, there would be a bump around the correct location. So for example, in here, most of the nearest neighbors are voting somewhere in the Utah desert, which is in fact the correct answer. Okay. So again, super simple method, worked surprisingly well. Now, fast forward 15 years later, neural networks became all the rage, and folks from Google decided that they're going to repeat follow-up on our work, but instead of the nearest neighbors, they're going to use a deep network. Okay. Also, because they're Google, they had much more data, so they used 91 million images instead of 6 million images. Okay, and they got much better results. Now, luckily, or maybe unluckily for others, I was one of the reviewers of the paper, and I was like, wait a minute here, you're changing two things at once here, right? This is not apples to apples. You're going from the nearest neighbor classifier to a deep network, but you're also increasing the number of data. So can we do an apple-to-apple comparison? Can you do your algorithm on our data set, on the 6 million data set? And the authors, very nicely, they did the experiment. And what we find is that actually, if you keep the data constant, it turns out that our silly, simple nearest neighbor baseline worked just as well, and in some contexts a little bit better than the fancy schmancy large neural network from Google. Okay. So I'm not saying, forget neural networks, forget transformers, everybody should just use nearest neighbor. That's not what I'm saying at all. What I'm saying is that in the competition between the algorithm and the data, you must not forget about the role of the data. And in this particular case, the neural network didn't need to do anything very smart. The neural network really just needed to memorize a lot of data, and it turns out that a simple nearest neighbor algorithm would do just as well. Okay, so the good news is the really stupid algorithms plus lots of data give you this unreasonable effectiveness. Okay, but surely, the human brain can't remember so many images. Surely this is not at all practical in the biological world. And here I would like to show a wonderful, wonderful experiment by my dear colleague Odd Oliver from MIT, a psychophysicist. This is quite an old paper. I think she doesn't talk about this anymore. This is from 2008, but I still like to advertise it because it made such a big impression on me. And basically, what she was interested here is to try to understand the limits of the visual of capacity for the visual long-term memory in humans. Okay, so I can give you a little bit of a background. Standing in 1973 did an experiment on human visual memory capacity. He showed subjects 10,000 images, and then he asked them, have you seen this image, yes or no? And he got a very high recognition percentage, 83%, which was quite amazing. Okay, so basically, we already knew that people could remember thousands of images. But what was not clear is how much of each image the people remember. Because the standing images, that they were very, very different. One was on a beach, the other was of a house. And so it wasn't clear. Maybe the people were just remembering like a keyword, or maybe they were remembering just a few sparse details, or maybe it was a really much more detailed thing. And this is what Odd decided to, and her students decided to study. Okay, so what they did is they did a massive memory test where they showed thousands of images, but the images were much harder. They were not. They were very similar to each other, and they might also be maybe the kind of different categories, but also the same category, different exemplars, or maybe even the same object, but in different state. For example, on the right here, you see a different state. Okay, and the task is to try to remember them all. And to make this interactive, and Odd has kindly given me some of her slides from this, we're actually going to try to do this experiment live. Okay, so I'm going to show you a very rapid sequence of images. Okay, and your task is to remember if you have seen it or not. And then if you have seen an image twice, if you have already seen an image, you're going to clap. Okay, so hopefully everybody can do it at home who is watching, and in the audience, maybe if we're lucky, we can hear some clapping in the recording. Okay, so if you see something that you've seen before, you clap. If you see something new, you don't clap. Okay, are we ready? It's going to be fast. Okay, 1, 2, 3, go. All right. So, unfortunately, I could not hear the clapping from the audience.
There was a
But-
lot of unanimity. When they got it, they all got it.
Yes, exactly. That's usually the case. There's a lot of unanimity, and what she did afterwards is she did these kind of tests afterwards. We can do that too. Which one did you see, A or B? Okay, it's A. Which one did you see, A or B?
A.
Very nice. I can hear that. Notice that they are very similar. They're both black remote controls. Okay, so it's very impressive. A or B?
B.
It's actually B.
They don't
Okay.
agree.
Okay, so I think by now you're already kind of getting a little bit of a sense of how the results are going to come out. But here are the results. So the first test is basically novel categories, and this is basically replicating the standing result. And here, Odd found that it was even better than standing, 92%. Okay, and what do you think will happen on the harder tasks, on the exemplar and the state changes? Is it going to be chance? Is it going to be the same? Is it going to be, half a performance? Just think about what you would expect, given that you just did the experiment. Okay, and turns out there's a little bit of a drop, but just a slight drop. It's basically almost as good. Okay, which was to me extremely surprising. Okay, because this suggests that it's not just compressing the images into very small code. It seems like it's representing quite a bit of the visual content. That's quite a lot of information is getting retained. Okay. Questions at this point? I should make sure that people, if you have burning questions.
Anybody from here or on the? Let me just check. In the attendees, there aren't any. I don't see any.
Okay.
Okay. By the way, I have a question.
Yes.
What happens if you include both variants and then ask them both variants?
Oh, I see. Both I don't know. That's a good question. But presumably, I think it should be able to tell both of them. But I don't know. Yeah.
Yeah. Oh,
I'll show you.
the camera is on the, yeah. Okay.
Gary Lupian.
Yes, and maybe we can talk more about it during the panel. But Talia Konkel, who's on the original paper, also
Yes.
has a follow-up paper where they do this. So Stefan, to include both in the training set.
Yeah.
Yeah, and so as you might expect, if you have a bagel in the training set, if you have more bagels, people's abilities to say which of these bagels in a forced choice goes down. What's interesting is, and this was the point of their paper, what predicted how fast it goes down? Is it visual similarity or is it semantic similarity? And it's not visual similarity. That's the finding.
What is the vocabulary for bagel differences?
Right. So you can, for example, have they contrasted things like exercise equipment. Okay, so things that look similar but are functionally different, things that are functionally similar but visually different, or butterflies, very visually distinct, right? But they're all butterflies, and unless you're an expert, they're all butterflies, right? So conceptual similarity predicts a steep drop. Visual similarity doesn't matter so much. It's hard to
don't let yourself be influenced. Conceptual similarity is a wishy-washy thing, but what you can say is that if it's not form similarity but category similarity.
Yes,
Okay,
yes, but
right.
it speaks to Alexei's point, right? That there's no such thing as semantic similarity without prior memory, without prior knowledge.
Right.
You have to know which things are.
Okay.
That's right. In fact, there is a little also, I think it's unpublished follow-up, because my first question was like, wait a minute, does this mean humans have photographic memory? And so I will do a little a follow-up experiment for you. So this is by Phil Isola and Odd, where they said, okay, well, let's do something that is not poisoned by by semantics, by categories. Let's take some visual textures, something like this. This is a Partila and Simoncelli texture synthesis results, and let's see how well do humans do if we intersperse the kind of natural images with images that are where the statistics are matched to look like natural image statistics, but the images themselves are random. Okay, so let's do a little bit more of clapping. Okay, are we ready? Let's do this. Okay, so as you probably already noticed by the disagreements in the clapping, basically what they found is that for these texture images, the performance was basically a chance. So people were not good at remembering some random texture. So this
there was a lot of agreement, but it was social facilitation.
I see.
Did someone do it and then they joined.
I see. So basically this also speaks to the point that it's not that we're remembering every pixel. It's not that we have photographic memory. There is definitely whatever memory is being done, it's done in some feature space, in some learned kind of latent space that is kind of connected to the prior experience. Okay, but that it's still, the capacity is quite tremendous. Okay, so this is all kind of old stuff, and I talked about the great kind of method, raw memorization methods like nearest neighbor. But of course, this is not the whole story. Okay, the raw memorization gets you quite a bit of the way, but it definitely doesn't get you all the way, especially in what we call the long tail events, right? So the rare events, there is a lot of them, right? The long tail of the distribution is very, very long, and most of the weight is in that long tail. Most things are rare. And so for most things, you're just not going to see a perfect match in your memory, in your data set. And I think what's been really impressive with the modern large generative models that we are seeing right now, both in text and in images, is how well they're able to interpolate and to compose data from different sources together. And here I'm just showing some of the images, image-based methods that have been very exciting to see. And so you get this impressive compositionality. So you never seen, a dolphin in a spacesuit in any of the training data, and yet it's able to compose together an image where different pieces of the data set fit well nicely. Okay, so that's absolutely exciting. But are we falling into kind of a similar trap where we are again focusing on the amazing algorithm and maybe the fancy language features, and we're kind of not really talking about the data that those methods are trained on, which is really enormous, billions and billions of images. Okay, so here is a little experiment that I done with 3 very, very different text to image models. So here I give them a prompt, squirrel reaching for a nut, and these are 3 methods that give you results. And the algorithms behind these three methods are very, very different. So in a computer vision audience, I would actually ask the audience to guess which image was produced by which method. Here, I'll just tell you, the first one is a diffusion-based DALI, the second one is autoregressive, PAR-T, and the third one is a kind of a large GAN model, the GigaGAN, okay? And now you can say, you like one over the other, but I think we all agree that, all three are doing something quite cool and reasonable, okay? Even though, again, the methods, the algorithms are extremely different, okay? And so this is a slide from my former student, Tae-Sang Park, who basically said, okay, let's plot the quality of the images. Here it's measured by FID score, the lower the better. The quality of the resulting images based on the model size. How many parameters does a model have? So on the x-axis is the number of parameters in log scale, okay? And the number of parameters is essentially how much data can the model absorb, right? The more parameters, the more data the model can retain, okay? And what we're seeing is kind of a nice linear dependency that no matter what is the algorithm, what we see is that the larger the model, the better the results, independent of the actual algorithm being used, okay? So again, we're seeing this a little bit, that it might be more about the data than about the particular algorithm that we are working on. And kind of another interesting point here is now these generated images are really, really impressive. These text-to-image models, for example, you give it a prompt, a green creature made of leaves and vines bursting out of the ground, ready to attack, blah, blah, blah. And boom, it gets us, this is stable diffusion, and it gets us something really, really cool. And, it feels like it's very novel and very creative and very, very different from whatever was in the training data, right? So we say, wow, there's so much kind of novelty generation being done here. Now, we last year published a paper on visual data attribution. The goal of the paper is to try to understand which images from the training set are most responsible for the particular generated image, okay? And what we found, and I'm not going to talk about the details of the paper, but just show this as a result. So for the image on the left, the following 6 images on the right are all in the training set. They are all in the Lion data set, okay? And these, our algorithm decided were the most influential images to generate this image on the left. Now, whether this is correct or not, we don't know. It's, this line of work is still in its infancy. But I think kind of the interesting point here is there is a lot of data in the training set that kind of looks like the generated image. So the generated image did not come out of the blue. The generated image was definitely has a lot of the ideas for that image came from the training data. They were actually in the training data, okay? And this is something that we don't quite realize because, with 5 billion images, it's very hard to actually look at them. So no human has actually ever looked at all of the Lion data set. But with these methods like this data attribution, we are able to kind of examine those images, and we realize maybe it's not that surprising. It's still kind of very cool that that the model is able to generate this image, but maybe it's not as hugely surprising as we thought originally, okay? So I like to paraphrase Arthur C. Clarke here. So interpolation in sufficiently high dimensional space might be indistinguishable from magic, okay? And actually, I really enjoyed the talk by Misha last week, who talked about maybe that space isn't even that large to begin with. And so here I wanted to bring back some findings from the 90s in computer vision, where we find that we learned that for the very specific class of human faces, it turns out that if you have, as little as a few hundred training faces in your data set, you can basically generate any other face on Earth by just linear interpolation. Okay, it's really a linear space in faces. And so what we see here is that there are much more people on Earth than there are faces, right? And this kind of suggests that on one hand, it's all about the data. On the other hand, maybe our world is, more regular and lower dimensional than maybe we kind of expected. And that might be another example of another explanation for kind of this unreasonable effectiveness that we are seeing. And since I'm talking about this, let me advertise a little cute little version, kind of a modern version of this idea that we are going to archive it actually tomorrow, I believe, where we basically show that you can do the same kind of find linear subspaces if you, instead of looking at the database of images, we are looking at a database of models. So we have about 60,000 diffusion models. And what we find is that we can also linearly interpolate. In this case, we can linearly interpolate the weights of the models and basically generate new networks by linear interpolation that are able to generate new faces. Okay, so here we are not training a model, we are just interpolating from the training models. Okay, so this is kind of like, instead of a data set of images, we have now a data set of models. Okay, so this is going to come out, I think, tomorrow or day after on archive, if anyone is interested. Okay. Okay, so let's now talk about kind of something that's also been very interesting to me. So, okay, with enough data, the algorithm might not even matter that much. But I think another thing that we're seeing is it might be that even the task you're trying to do doesn't matter. And now this is something that I think LLMs have really kind of opened our eyes in the computer vision community. This idea of prompting or in-context learning. Okay, so we definitely have some GPT envy here when we see something like this. The prompt is a piece of French and then some English, and then even GPT-3 can basically not only do the task of translation from French to English, but it understands what we are trying to make it do. So it basically it understands the task simply from the prompt. You never train on the task of translation. Okay, and so we said, oh, this is such a cool thing. Can we do this for visual data? Okay, and I believe this is a really important thing that organisms should know how to do. Okay, so basically, this is a paper we did a couple of years ago where we thought, okay, can we formulate visual prompting? Okay, and how would we do that? And here the idea is actually a very old one, comes from 20 years ago, on this idea of visual analogy. So if you have taken one of those standardized tests, you might remember this kind of analogy. A as to A prime as B is to what? Okay, so this is a visual analogy. And so we thought, okay, maybe we can formulate visual prompting as a type of analogy. Okay, and you can imagine that you can basically define many different tasks, visual tasks, with this kind of analogy formulation. Okay, so how are we going to do this? And again, as is often in my work, you just think of the simplest, dumbest thing to do, and you just try it with lots of data. Okay, and so the simplest, dumbest thing that we did is we basically took these 4 images, put them all into one larger image, and then basically just fired up an in-painting model, a hole filling model, in this particular case, a masked autoencoder, to fill in the rest of the image. Okay, and kind of magically, it was able to do reasonably well. Okay, so here is some wide range of tasks. We did not train on any of those tasks, and you can see that it's basically doing kind of reasonably well. Now, it's not winning any awards for performance compared to specialized methods, But the fact is that we didn't tell it anything. We just okay, just fill in the hole, and it was able to do this. Okay, and kind of the only difference that was important is that the training data needed to be a little bit special. So like something like an ImageNet data set was not good enough for training. What we did is we actually scraped figures from 20 years of computer vision papers on arXiv, and we trained a hole filling algorithm on random patches from these figures. Okay, so my theory is that what it really learned is it learned this idea of a grid of figures. So in computer vision papers, we always have grids of, okay, here is how the same algorithm works in many different images, or how the same image works with many different similar algorithms. And so I think basically these grids taught the hole filling method about analogies. And then once it understood the analogy idea, then it was able to do this task. So that's basically my theory. But what we saw is that it was actually working well on things that were quite out of distribution. This was not in any of the computer vision papers, and it was able to do reasonably well on these kind of tasks. Okay, and here is some more. And of course, you can see that sometimes it really doesn't work. So it's not complete magic. It does make silly mistakes, but the fact that it works well at all is, to me, quite surprising. Okay, and let's see how much. Okay, 5 minutes, perfect. And so the only problem was that we really believe in scaling. We really believe in giving more and more data. And what we found is this masked autoencoder, the hole filling approach, didn't seem to scale that well. Okay, so we wanted to give it more and more data, and it basically the performance just wouldn't budge. At some point, it stopped improving. Okay, and this is where we decided, okay, maybe 25 years later, I'm going to go back to my roots and go back to autoregressive modeling, because what we have seen in text domain is that these LLMs are really, really good at scaling. Okay, and so in this paper that's going to be presented in CUPR in a couple of weeks, what we said is, okay, we're going to take a large language model, but without the language. So we call it large vision model. Okay, so the idea is that we're going to do everything that the language models are doing, but instead of language, we're going to have visual tokens. Okay, so we're going to have lots and lots of data, and we're going to have an autoregressive architecture, and we're going to basically do this next token prediction, and we're going to evaluate on prompting, just like a language model. Okay, so we just decided to put together all the data sets that were available to us in computer vision, put them all together, but we didn't want to have any semantics in it at all, or at least no semantics that were expressed as language. So we basically only encoded pixels. So some of the images were just single images, and then we basically just tokenized it to represent an image as 256 tokens, or it was a series of images, a video. So you kind of have a visual sentence of a series of frames, or it was image sequences. So we kind of take a image, take an object and rotate it over time. We also did some ImageNet categories, so there is a little bit of semantics in there. And we also put in all kind of all the annotations that we could get our heads of in terms of all the data sets that we have. So for example, here is the human key point annotation, and then we also have various things like object detection and colorization, depth estimation, whatever. Basically, all the data sets we could get our hands off, we put in there, but they're all in terms of pixels. There is no other data source rather than pixels. So the data stream is basically a stream of visual tokens. And then we just trained a standard llama model just like you would train a large language model. Okay, so it's basically very, very similar, except the data, the tokens, instead of being tokens from text, they're tokens from pixels. Okay, and we are now seeing that the scaling behavior is much, much better than what we have seen before. But of course, the cool thing is now we can prompt it as you would prompt a language model, but we can prompt it now with images. So we can give it a series of images, the context, and then we can say, okay, what comes next? Generate the next series of tokens. And it kind of naturally just does, video prediction. Now, it's not that exciting a video prediction, it's just one frame, okay? But it seems to be doing it. And we actually also try to make it predict, several frames. So in this case, it's 4 frames. And, it's starting to do something reasonable. Now, this is, of course, much less exciting than if you do it on text. But remember, we're working with very, very low quality, noisy, high dimensional visual signal. So we can't expect real magic to appear. But we do see things like, okay, if you start rotating an object, the model learns how to continue rotating it. Or if you prompt it with a task, like an analogy task, like, okay, can you find the skeleton for these people, and then give it the last image, it will do the annotations for that last images, again, kind of out of the box. Okay, and we can do it for all sorts of different tasks. And we can also see that we can kind of combine things together. So here, for example, the task is rotating an image, but we also labeled the card wheels here with the red circles, and then we give it a new set of car images, and they say, okay, continue that sequence. Okay, and the nice thing is that it continues rotating the car, and notice that the prompt car is a synthetic car, and it only sees synthetic data at training time, but actually it's able to do it for a real car. But it's also able to kind of continue keeping those key points attached to the wheels as well. And then we do things that try to do tasks that it hasn't seen before. For example, a relighting task, and it seems to do reasonably well, or tasks that we don't even know what it's supposed to do, but it does something interesting, something like that. And then we kind of got really cocky, and we said, okay, what about we try to do something like the Raven's progressive test? So there's kind of a classic non-verbal IQ test. Okay, so you get a sequence, a matrix of shapes, and then you say, okay, which of the shapes should go into the question mark position? And the way we did this is basically just made it as a hole filling exercise. So we prompted the system with the hole filling example. So we say, okay, here's how you do hole filling, and then at the test time we say, okay, here is some of these Raven matrices, fill in the hole. And sometimes it actually does pretty well. Now, it's also doesn't work plenty of times. So this is not, I'm not going to claim, sparks of AGI or anything like this, but the fact that, sometimes it works is kind of encouraging. Okay. Even especially since this model that we have now, it's probably the largest large vision model that has ever been trained on it. But in terms of the size of models compared to language models, it's tiny. It's something between like GPT-1 and GPT-2, right? It's really not that big. So the hope is as we push more and more data through it, things will only improve. Okay, so I think I will finish here. So to summarize, bottom-up emergence of intelligence from raw sensory data is, in my view, a worthwhile goal, and a number of us are kind of pushing in this direction, although it's going to be a long and lonely slog because the data is so much less informative than top-down data. But we do need to remember to be humble and to give data the credit that is due, and not get too cocky and not think that we can do everything with our clever algorithms, because data might not be sufficient to do well, but from all that we know, it is absolutely necessary. Thank you very much, and I can answer questions now.
Okay, so now you're gonna, you don't hear that there's applause going on now. I didn't realize that the applause couldn't be heard, but you were just applauded. Now, we're open for questions. There is one by Jan, just a second, Hookinen. Do you want to ask your question?
Yeah, sure. Can you hear me?
Yes.
Yeah, this might be a little bit like an eclectic question, but on the other hand, it seems that if we have huge networks, they're kind of just memorizing all the huge data sets. But on the other hand, we have the universal approximation theorem, which would kind of imply that even large net could be compressed to small ones. But is it compressing the large nets impossible because they seem to kind of remember all the data?
So as I have shown in this random noise experiments, at least it looks like, you know, most humans don't have photographic memory, and we don't remember everything. So there's definitely some compression going on, absolutely. And I believe that even in the modern networks, there's probably going to be some compression that will happen, some sort of distillation methods or things like that, that probably will get, you know, maybe 10x or maybe even 100x compression of the current systems. But despite all this compression, we still need a lot of data. So we might be able to handle less, you know, more compact models than we have right now, but they're still going to be huge. So I think that we cannot escape from just needing a lot of data, because what we're interested in is a biological phenomena, and the biological phenomena just has a lot of entropy that is important. Okay, and I think just because of that, we will not be able to escape having to have lots of data fundamentally. But I do believe that, you know, as is often the case with algorithms, and you know, the first attempt at something is going to be too large and too clunky and too slow, and then people are going to figure out how to make it faster, better, smaller, etc., etc. So that will happen, absolutely. But I think that will not, you know, it will not completely get rid of data. I truly believe that data is going to be the one thing that will be constant as the algorithms change and as our field evolves. We will still have to have data.
Do you have access to your Q&A display?
I do, but you know, the reason I do computer vision is I don't see very well, so it might be hard for me.
I'll do it for you.
To read, yeah.
Sayara Islam, sorry, I skipped one. Julia, you can, I'll give Sayara's answer, and meanwhile I'll bump you up so you can give your own. Can Sayara Islam ask, can simple models like K nearest neighbors create novel images like diffusion models given a large data set?
Yes, very, very kind of interesting question. So my texture synthesis work from you know 99 was exactly that kind of method. So you basically you take little patches of images, and by doing an autoregressive method, you can create images that has never been seen before, because you're combining patches in novel ways. And if you know a content-aware fill in Photoshop, for example, that has been around for 15 years, that's basically the idea that they're also using. So it's definitely possible. It's definitely possible, because you're basically kind of doing compositionality, kind of forcing compositionality by saying, okay, I'm not looking at the full images, I'm looking at patches. And there are also other approaches that, for example, the Gaddis approach, the stylization work that was very popular a few years ago, kind of where you force statistics of an image to be the same. It's definitely possible. Now, if is that the right thing to do right now? Maybe not. But I don't think there is anything that says that you cannot do this. In fact, it's kind of interesting that something like a diffusion model, the objective that it's trying to optimize for is to memorize the training data. So if the diffusion models were doing what they're told, they would only be able to produce images from the training data. And it's kind of interesting that, the reason that they're working so well is exactly because they're not completely optimizing the objective that they're told to optimize.
Okay, Julia, you can ask your question directly.
Hello, thanks for the talk. So I was just wondering, when you generate the visual tokens in your large vision model, is it one tokenizer for both generating the vocabulary and then also mapping the input to tokens? Or is that like broken out? And then is the basic unit the pixel, like the byte for most LLMs? And how big is the vocab?
So the tokenizer is kind of a separate thing, and we train a tokenizer on lots and lots of data. Although I think right now we switched to a kind of an open source tokenizer. The unit is really kind of an image. So we have 256 tokens per image, and so they're not like spatially. It's not like patches or anything. We're just kind of getting a set of tokens for a single image. The size of the vocabulary, I don't quite remember, but the paper is on arXiv, and it's and you can, and hopefully we will release the code Friday, hopefully, or at least before the conference starts next week. So we're going to release it before the conference starts.
Thank you.
Yeah.
Okay. Other questions? I'll fill in, I guess we're not out of time, and I'll fill in the gap. One question about unsupervised learning and another question about evolution. First of all, is it like if you say data is everything, does that mean that you're putting most of your faith in unsupervised learning?
Okay, so I'm not saying data is everything, although I guess that's maybe kind of true by default because there was not anything else, right? If we are evolutionists, if we're not creationists, there wasn't anything else but the data to begin with. So I guess in that sense, maybe it is everything. But I guess I'm kind of, in my talk, I try to say, okay, data is something that people are still not giving enough credit to, and we need to kind of keep thinking about it. In terms of unsupervised, well, okay, a lot of my work has been on self-supervision. I kind of push self-supervision to be popular again in at least in computer vision, 10 years ago. And here I think kind of it's similar with what Misha said, that self-supervision is basically using the machinery of supervised learning, but without the labels given by humans. So I'm against human labels, okay? Now, I would argue that the world is the best supervision we have. For example, time is fantastic supervision. Now, one of the most important tasks is prediction task. And the prediction task has a beautiful natural supervision. You predict something is going to happen, and then you just wait. And then you see, does it happen or did it not happen? So to me, that's supervision. But it's not supervision by a human. It's supervision by the environment, by our Umwelt. So I'm very much into this kind of natural supervision or self-supervision, because the methods that are supervised methods just work much better than the kind of classic unsupervised methods.
I don't know if
Sorry.
I don't know if you heard when Dave Chalmers mentioned the example of, well, it's all for reproduction, etc. The ultimate supervised learning is evolution is reinforcement learning.
Not quite. I would not agree with that, because to me, the most exciting thing about evolution is that it does not have an objective, right? Or rather, the objective is not stationary. The objective changes over time. And at least reinforcement learning as it's done right now, you have a fixed objective and you're stuck with that objective. And I think that's actually the really fundamental difference. I think the real exciting thing about evolution that we don't quite know how to get to is the fact that the objective itself is an emergent property.
Well, Chalmers was right when he said reproduction, because that has to be the bottom line. If you ignore that, you're not going to pass on whatever you're selecting.
Yes, but when you start actually coding it up, you say, what is a reproduction? Because the copying is noisy. So how do you know that your offspring, is actually, because it's not a perfect copy, right? So actually, like when you start writing it down, you realize it's actually really, really hard to make it work, right? And then how do you want reproduction, but you also don't want a stone that just always there. It's also evolutionary very successful, right? So things are tricky. We're
running out of time. That's not over, but Steve Hansen has a question. Just go ahead, Steve. Turn on your face.
Hi. Yeah, I enjoyed that quite a bit. It was a great talk. And I agree with you that, data is often undervalued in these stories. And it's very clear if you look at GPT-4, we're talking 1 trillion tokens. Okay, so GPT-5, what? When are we running out of data? And in some sense, you're correct about there has to be some kind of selectivity here about the data. In other words, if you were a memory learning something, it'd be nice to know what it is you'd like to see next. And of course, with bodies and heads, we can walk around and look at things, and poor chatbots are stuck just getting this text. We also know that human memory just isn't like this. So there's roughly the estimates is between 5,000 and 10,000 faces that any average human can recognize. And it's also clear if you look at brain imaging data, Chantal Stern and some other people in the early 90s showed hippocampus actually becomes active whenever it sees something novel. So that's important. In other words, there's a network of systems in the brain in terms of object recognition and novelty detection. So in fact, it can say, I'm just not going to look at this, okay, because it's not novel, okay? And so that's actually a very important part of this. We don't know. We don't know if chatbot has any of this, but I can certainly guess if we take this strategy of taking as much data as we can get, there's a sense in which we're running out of data. And I don't understand what that sense is, but it's a crisis, I think, for OpenAI and Sam Altman to figure this out, because they've been delaying GPT-5 for months and months and months now. And I suspect there's asymptotic reasons. So I'll stop there.
I completely agree with you. I think in terms of text, they're going to run out of data because they have already all the high quality data. Now they only have the Twitter and the Reddit, and that's not going to be good data. That's where I think we are going to come in and say, well, guess what? There is infinite visual data, and there's infinite robotic tactile data. And I think that kind of multimodal data will become much, much more important next because we're going to run out of the textual data. In terms of finding the right data for us, I completely agree with you that I think that, and this is where I think embodied data collection, where you're having robots that collect the data that is useful and interesting, is very important. And we had a paper that was actually I listed it. I didn't have time to get to it on curiosity, which is exactly a mechanism we showed it in playing video games. So basically having a video game with no objective, but just figuring out how to play a video game by just being curious about the data that you collect. And I really believe that this is the future, that we will have to, instead of just downloading data from the internet, we'll have to go into the real world and have some sort of an intrinsic motivation, curiosity-based mechanism of collecting our own data. And absolutely, I think this is going to happen quite soon.
Okay, Jan, you have 2 more minutes if you want, if you still have something you want to ask.
Yeah, sure. I was thinking, like the images in the dataset, they're kind of discrete snapshots of our real world, but our real world, especially from the perspective of a child, it's kind of continuous. So would there be any kind of help for the models to kind of model the world if there was kind of some kind of constant video stream for a robot or whatever, so that the true statistical nature of our 3D world would be kind of available for the models instead of these image patches of different images?
Absolutely. I think static images is an illusion. This is not actually how we humans see the world. We see it in patches based on the visual saccades. It's a stream of visual data. The main problem is basically just we don't have access to high quality visual streams of data. You can go download things on YouTube, but it's very, very noisy data, and it's not really very it's very different from kind of an everyday data that we have. So maybe 10 years ago we were all excited because the Google Glass was going to come out and everybody was going to wear these Google Glass cameras and we'll get all the data we want. And of course people hated it. Nobody was wearing it, and so we never got the data. There is some attempts to get this kind of visual data. The egocentric data sets are coming out, like Ego 4D, for example, out of Facebook. So things are getting better, but I think right now it's still, and it's very nice. You can actually see, like, the more data something has, the better it works. So, text has the biggest data right now, and LLMs perform the best. Images is the second biggest data, and they do pretty well. Videos, not much data, and the video generation is, there is Sora, but it's lagging behind. And then in robotics, there is basically no data, and it completely doesn't work. So once again, it's all about the data. Yes, and we do need to have better video data if we want to make progress. I totally agree with you.
My eyes missed me. We have 10 more minutes still. So we have Gary again, and we also have Michael and Anna and Valerie who want to ask questions.
Yeah, so touching on your last response, so in a lot of vision models, language plays an important role, right? So yes. Of course, with supervised models, right, where the labels are linguistic, but also with a lot of the generative models, there's language in the loop in the form of captions, and arguably it's playing a key role in being able to make sense of the visual data, not only because we want to be able to prompt the model with language, right? But a lot of the kind of that magical power of compositionality, arguably, and that's the question to you, from my side, it seems that language might be doing a whole lot, right, in helping the model form more composable categories, right?
Right.
And so I'm very curious how you see this. So the last part you talked about, the large vision models, I guess, there isn't language in the loop in the sense of words. Arguably, there's indirect influence of language in that, participants are being, or researchers are they're doing particular tasks, right? That can't be gotten just from naturalistic observation, right? At least not directly. But yeah, how do you think about this? So is it just that there's more data, or that language is a kind of a different type of data?
Right. No, I agree with you. This is a very, very good question, and I don't have a very satisfactory answer. I am biased against language for my own work. not because I don't like language. I'm a great fan of literature, and I love language. I just feel that in computer vision, we're just not ready for it. In robotics, we're not ready for it, because every time you see language and vision come together, language dominates, and language does most of the heavy lifting. And so if we're interested in this kind of evolutionary story, I am interested. I don't, my goal in life is to have a, artificial, I don't know, squirrel or a mouse or a rat, which, the visual system of a rat is like, would be my dream if I could kind of get to that level. So I am interested in what can you do with before you get to this high level semantic story. In terms of how much of the lift is being done in terms of compositionality, there's definitely some. But what made me very excited is that some of the results that we see in diffusion models, for example, for hole filling, show that a lot of the compositionality is not textual at all. For example, the fact that the shadows align, right? This is never spoken to in language. This is actually very hard to describe in language. And yet, the diffusion models are able to make the shadows align, make the lighting consistent, make the the things that are materials, like how does a plastic look like? This is something that's extremely hard to describe in text, and it seems to be doing very well. So I think there's definitely a lot of the lifting in compositionality is done in text for the kind of things that are in your prompt. But we're also seeing compositionality that is not linguistic emerging in the diffusion models, and also in the model that the large vision model that we showed. So I'm hopeful because if it's all just language, then how do we proceed? It's like, in that sense, we already have the answer, but how do we get to the answer in the first place? So I'm hopeful that we will be able to get this kind of compositionality to emerge from raw signal directly. But it's an open question right now. Absolutely.
Michael, turn yourself on. You have a little niche. Okay.
Thank you for the talk. The paradigm of SSL has been mostly using kind of existing data that's been, scraped from the internet.
Right.
In recent kind of RLHF and always in RL, we find that on-policy data is key. So data that your model itself has generated.
That's right.
Do you think we're going to move from a paradigm of high-quality offline data to a paradigm of high-quality on-policy data and high-quality interaction? And what is high-quality interaction?
Yeah, no, I absolutely believe that. So the one paper I didn't get to talk about is our work on curiosity. That's it's a few years old now, but I do recommend that you look at this. It's called Curiosity-Driven Exploration by Self-Supervised Prediction. So it's basically it's a self-supervised method, but it creates its own data by exploring the world. In that case, it was basically the world of video games, and all of our attempts so far to try to port this to real robots have failed. I'm not giving up. We have a project this summer to try to do it. I think it's possible. We also have approaches that basically try to do this in the world of internet. So we have a paper called Internet Explorer, where basically we have an agent that goes onto the internet. It's like RL, but on searching for the right training data to train itself. And absolutely, I do believe that we should be moving away from this idea of a static data set. The world is dynamic, the world is ever changing, and we need to have methods that are basically online, lifelong, collectors of data. And we humans, we are that. And all animals are basically online data collectors. All we do is we collect data, we collect experiences, we collect knowledge. We're not given a data set. And there is, of course, a lot of issues to be solved here. For one of my perennial thorn is the fact that all the methods right now, they require data to be IID, right? Which is not something that in nature ever happens. In nature, the data is always a sequence. It's always correlated. And at least I don't know how can we make our current approaches work with streaming data that's not IID. All right. So if anyone has any ideas on this, I would love to know. This is a big problem for me, because I would love to train on just streaming data, but current methods just don't work well.
Okay, I've bumped up Anna and Valerie, but don't worry if you don't get a chance. And Jan, you'll get another chance in a half an hour. It's going to be the panel, but I don't know what order to call on you in the short time. Who wants to, Jan, you were going to say something again?
I'm sorry.
Yeah, sure. I was.
Sorry.
Yeah, this is
Go ahead.
This is the disorder that happens when I can't specify. Well, who said that? I don't know who said that. Anyway.
Yeah.
Go ahead, Jan. Go ahead.
Yeah, sure. Kind of related to that. This is maybe a naive question, but in backpropagation, the most error comes from the long tail of the images. And on the other hand, if you have a lot of correlated data, then the error is kind of small, and the network is not learning much. So why do we have to have the IIT balanced dataset?
Okay, my understanding is that the main problem with non-balanced data is that it's you forget the old stuff, right? You get what's called catastrophic forgetting. You overfit on the here and now, and you forget what you have seen before. So the IID forces you to kind of keep rehearsing the stuff that you have seen from a whole bunch of different places. That's at least my understanding. But I'm not really a machine learning person, kind of not a theorist. So I think I'm sure there are people who have better answers. I want it to be solved somehow.
And maybe we can just filter out online the correlated data and just keep the long tail in a recurring training loop somehow. I don't know.
I mean, that's what people do, but I would, an animal sees the world presented to it in a very correlated way, and it's fine. Why can't we do the same?
Anna, you have one gasp, and then we have to turn it off. Go ahead.
Okay, thanks a lot for the talk. I really enjoyed that. And I have a question. So I don't have good reasons why I have the feeling that scaling up is not the only solution we should follow. But I have a worry. And this worry is mainly related to large language models where language plays a role. And what I observe at the moment is that we are not able to distinguish between machine-generated text and human-generated text anymore. So neither algorithms nor humans are really able to do that. And that means that the training data of future models are sort of polluted by all the outputs of the large language models. And we also know that the outputs of large language models are not reliable. And so the data get worse. Even if we have more data, they are more polluted. And so this is a worry I have for large language models. And I wonder, after listening to your talk, could a parallel worry happen for vision as well? So if you have many large vision models like you introduced in your talk, that they have many sort of false guesses what they do, and then you train the next generation on 40 stuff.
Right.
Then the scaling up idea is sort of buried, no?
Question is posed. Go ahead.
Right. No, it's I think we're much better on the sensory side than on language. I think I completely agree with you. You know, yes, large data is important, but if you're generating it yourself, you know, it's not there. There's, you know, you're not adding any more entropy to it. You're not adding any more signal. So yes, I think training on generated data is going to be a big problem. I think these large language models are going to run out of data very soon. I'm quite worried about that. I feel like with raw sensory signal, like, you know, vision, robotics, audio, I think we're much better off. There's just much more data, and the data changes all the time. So I think, yes, we could start training on, you know, Sora videos, and that wouldn't be good, I don't think. But I think we have much more access to raw data, you know, almost infinite amount of raw data if we look at these kind of sensory modalities like, you know, vision and touch and things like this. So
Okay.
I feel like, you know, this direction is going to be much more promising going forward, exactly for the reasons that you described.
Thank you. You will now hear the sound of 2 hands clapping, which you will not hear.
Thank you.